This is Gauss law of magnetostatics. Gauss law of magnetostatics says the flux of magnetic field across a closed Gaussian surface is always zero. If you take a closed Gaussian surface like this, the flux of magnetic field will be always zero, where n is an outward drawn unit normal vector to S. See, if I reduce it to differential form, let's try to understand the meaning of this. If I reduce it to differential form, I'll get it 0. Since the integral is 0 for volume enclosed by any arbitrary closed surface, so it means del dot B is 0. What does the divergence denotes? What does the divergence denote? Divergence of any field vector means source or sink. It means source or sink. Alright. It means the source and sink means at any point you do not have either source or sink, or I can say the isolated source and sink of magnetic field do not exist. At no point in space you will have only source or only sink, right? If you have a source, you have an equal and opposite sink also. You have equal sink also. Means wherever magnetic field is produced, if magnetic field is produced from here, the magnetic field will converge at this point also. If you have one line emerging out from here, you'll have a lines converging over here also. It means the source and sink of magnetic field, you can say the source and sink of magnetic field exist together. Magnetic field exist together, or source and sink of magnetic field is also called magnetic poles. So magnetic dipoles means north pole and south pole. You can say north pole is regarded as the source of magnetic field and sink of magnetic field is south pole. So magnetic poles exist in pairs. I can write the magnetic poles exist in pairs. You can't have magnetic monopole. You can't have only source or sink, or you can say the magnetic monopole do not exist in isolation. The magnetic monopoles do not exist in isolation. Where you have south pole, you have the north pole also. You can never have the magnetic field like this as you had in electrostatic field. You can't have this kind of magnetic field lines. It means you have the source over here. You can't have this kind of lines, or you can't have this kind of lines in case of magnetic field. There doesn't exist a sink. You don't have isolated source or sink. So these kind of lines are ruled out over here. You can't have the diverging field or the converging field at any points. At any point you can't have the field like this. Alright, means this kind of source or sink do not exist, right? Do not exist in isolation. You have this kind of field lines in case of electrostatic field, but you can't have in magnetic field. Magnetic field line we don't have magnetic field like this. So this kind of lines are ruled out. This kind of lines are ruled out. I can make use of this at one more place. I'll give you the corollary of this theorem. This law has got a corollary also, which says, I'll first write the corollary of this Gauss law of magnetostatics. See, the corollary is the flux of magnetic field across any two open surface bounded by the same curve is always equal. This is curve, CURV. What does it mean? If you have a curve like this, then suppose this is a surface bounded. See, what do you understand by bounded by surface bounded by a curve? See, every open surface has got a bounding curve. Every open surface, like you have a hemisphere. This is the bounding curve. The circle is the bounding curve of hemisphere. Bounding curve means periphery of the surface. Disk also has a circle as the hemisphere. So circle has the bounding curve. Cone is bounded by the circle, right? Sphere, complete sphere, it's a closed surface, so there is no bounding curve. Bounding curve is there only for the open surface, right? This is a hemisphere, bounding, this is the bounding curve. This is a disc, disc has got circle as the bounding curve. This is a cone, cone has got a circle as the bounding curve, right? One more thing, a single bounding curve, you can have many surfaces bounded by the same bounding curve. So this is S1 is bounded, if this is the bounding curve, S1, S2, even this disc, they all are bounded by the same curve. So for a given curve, you can have many surfaces bounded by the same curve. A single curve can bound infinite number of surfaces, you can say, right? Now the theorem says the flux of magnetic field across any two open surface bounded by the same curve. Suppose I take this as S1 and I take this as say S2, then I mean to say that the flux of magnetic field across any two open surface S1 and S2 which has got the same bounding curve will always be equal. See how we can prove it. I'll prove it mathematically also. Like, let me erase all this. Here I have to prove that the flux of magnetic field across S1 and S2 is going to be equal. Right. One more thing I will tell you before proving this. See, if suppose this is the bounding curve, this is the bounding curve, right? Suppose this is a disc, this is the disc. Then what do you understand by when you say normal to the surface? Normal to the surface. How do you define normal to the surface? How do we define normal to the surface? Say this is a disc, right? This is a disc, this is the bounding curve. Then what is normal to this surface? See, normal can be defined. You can have two normal to open surface. This is also a normal, this is also a normal, right? But how do you specify n? So your n can be in this direction, n can be in this direction, until you orient the bounding curve. But once you orient the bounding, if you don't orient the bounding curve, I can take n as this also. But once I orient the bounding curve, your n gets defined. Once you orient the bounding curve, your n gets defined. Suppose you orient the bounding curve like this. You put the fingers of right hand in this direction. Put the fingers of right hand along this orientation. The thumb is going to give you. You put the fingers of right hand in this direction. The thumb is going to give you the orientation of the bounding curve. I'll see it over here. This is your bounding curve. I think it's visible. This is the bounding curve, right? If this is n, if I orient this in this direction, then n to this surface, you put your fingers like this. You put the fingers in direction of orientation. This is the orientation. You put the fingers in direction of orientation. N gives you this n. You put your fingers in the direction of orientation. This n gives you the direction of the surface n. So once this will give you direction of normal to the surface. The thumb will give you the direction of normal to the surface. You orient the curve. The direction of, you put your fingers of right hand in the direction of orientation. Thumb gives you normal to the surface. That means once you orient the curve, your n gets defined. Once you orient the curve, your n gets defined. If I orient it in opposite direction, then the thumb goes inwards. So n lies inward. N lies inward. Alright. So once you orient this curve, once you orient this curve, you put your fingers of right hand in the direction of orientation. In the direction of orientation, n will be normal to the surface. This is going to be your normal. The normal is going to be this if you orient it in this direction. Right? Now, suppose I orient the curve. Suppose I orient the curve in say this direction. Suppose I orient the curve in this direction. In this case, now if I orient the curve in this direction. So in this case, see S1 and S2. Now I have to prove this. Keep all these things in mind, what I have told you, right? The proof from Gauss law of magnetostatics. See, first of all, consider a closed surface sigma. Consider a closed surface sigma consisting of, consider a closed surface sigma consisting of S1 and S2. Then from Gauss law of magnetostatics, your B dot NDS over sigma is going to be 0, or B dot NDS sigma consists of S1 and S2. See, in Gauss law of magnetostatics, it has been clearly defined N is an outward drawn normal. Outward drawn normal means outward from the volume. This is outward from the volume. This is outward from the volume enclosed. The volume enclosed by sigma. Sigma is S1 plus S2. So S1 plus S2 is enclosed in this volume. So N is an outward drawn normal, right? So, but for a given orientation, normal to the surface is this. For this surface, N lies in this direction. For this surface also, N lies in this direction. So normal to this disk is opposite to N, where normal to this S1 is in direction of N. So I can write this as, for S1 your normal to surface is same as outward or normal, but for S2 normal to this surface, I have oriented the curve, and based on this orientation I am deciding that normal to S1 and normal to S2 both. So normal to S1 will lie in same direction as N, outward or normal, but normal to S2 will lie in direction opposite to the outward or normal. So I can write this as, this N dash, which is normal to S2, can be written as minus of N, or we can write B dot minus of N, B dot, you can write N as minus of N dash ds. Say S2, this is S1, or we can write B dot NDS over S1 is equal to B dot N dash ds over S2. So the flux of magnetic field across S1 is equal to flux of magnetic field across S2, given they are bounded by the same curve, and the normal to S1 and S2 has to be taken as per the orientation of the curves. We are finding that the flux of magnetic field across S1 and across S2 is going to be equal. See, I can do it physically by using lines of field. Suppose this is the magnetic lines, right? Then flux as per the magnetic lines is defined as number of lines passing through the surface. So I can get this very easily by saying the magnetic lines, the number of magnetic lines across S2 and number of magnetic lines across S1 is going to be same. So flux across S2 and flux across S1 is also going to be same. So it's a good example, good application of Gauss law of magnetostatics. We will find its use also, right? So please remember all these things.